Hi, it's Terry Dennery of the MathWorks. In this video, we're going to get a little bit more focused on the real world again and the idea of how do you really implement such algorithms onto processors that can operate with real robots. Okay, we're going to introduce this term discrete. And I think if you really kind of break it down, perhaps discrete is kind of the opposite of continuous. It's sort of this idea of sampling and taking points in time and saying this is what it is and all that kind of stuff. And as you get into controls, you definitely start using terms like, well, what's the rate of your feedback loop? And you start talking about things like 1,000 hertz, 10,000 hertz, whatever. And the higher, the rate, the bigger the hertz number, usually the more expensive the hardware will be to produce such a system. All right. So from my perspective, though, I tend to think of discrete as almost meaning the same thing as fixed time step. And certainly the idea that you're going to do calculations, for example, on these PIDs. You can actually do numerical integration. I stands for integral, D stands for derivative, that you're going to be doing that sort of thing, right? But you're operating on numbers that in part are generated by hardware. That's the signal for angle for the turntable motor from the real robot when you implement this on the real system, right? And so as soon as you're getting into a calculation that's including real world, real-time measurements, the approaches of what you can do numerically will change completely. And that's where this whole idea of fixed time step, of course, becomes important. Because if you're doing a variable time step method, well, that's all based on the idea of going back and trying again if you begin to spot kind of a divergence in your calculation. So there's no trying again when you're operating on real hardware, right? And to do this, everything now needs to become fixed time step. All right. So anyways, let's kind of get into the specifics of this one is to basically turn all these PIDs into discrete. And certainly the PID block is very helpful because right at the top it says, oh, do you want it to be continuous or discrete? All right, so we choose discrete. As soon as you choose discrete, then you get into the idea of sample time, which is kind of implying fixed time step. All right, so -1 would be do whatever the solver of Simulink says. But for true implementation, when we generate this all into code, there will be no Simulink solver. And so this idea of locally setting it makes a lot of sense for a lot of reasons. But I am going to do it this way. I'm going to introduce it as a MATLAB parameter. I'm going to call it TS. You'll see, initially that block is like, well, I don't know what TS is, and that's because we haven't assigned it yet. And you'll see I've been practicing, so I'll just double click on that. TS is going to be equal to 0.001, 1/1000th of a second. In other words, it's 1,000 hertz rate for our feedback loop. All right, so let's get back here. And if I hit Control D, which stands for update, it's going to say, I gotcha. And that's because it knows it can go to that MATLAB workspace where it's finally finding something that's declared as T sub S. All right, so kind of the implementation of this is not so bad. And so again, you'll recall, and I made a point, when we got into this, that this doesn't happen without a good feed-forward controller, right? But that we were somewhat, I'll call loose and maybe a little bit arbitrary in just choosing a value of 10 for the proportional gain, 0 for everything else, and that we got it to work with that too, right? And again, it's because we had a good feed-forward controller, right? So let's just kind of continue on that path. We'll just kind of copy this in for each of them. Okay, and let's run it from the animation. So I'll hit that arrow in the upper left-hand corner, and that didn't work out too well, right? So 1,000 hertz seems bad, right? Well, it absolutely is bad. I'll assure you of that. All right, so anyways, one strategy would be, I'll do this one right here. TS is equal to TS divided by 100, so we're down to 10 to the minus 5 now. I am going to hit the run button, and I will be quiet. We're going to let it calculate, and I'll come back and we'll watch it in playback mode, but I can assure you it works pretty well if TS is equal to 10 to the minus 5. But while we're here and we're watching a simulation that's trying to run at 10 to the minus 5, well, we'll see we're doing essentially 100 times as much calculation, and we're running into the limits even of what my laptop is capable of doing. All right. And I'd say we can probably get 10 to the minus 5 to work on a embedded processor, but you are beginning to push it at that level, right? And certainly my laptop is probably struggling as it tries to push the mechanical dynamics calculation through at 10 to the minus 5 too. So anyway, speed is important. So anyways, let's let it run for a little bit, and I'll come back in a sec. Okay, so let it run for about, what is that, 5.5 seconds. So I'll just kind of show in playback mode that for a sample time of 10 to the minus 5, works beautifully. Again, if you think of how numerical integration works, hopefully it kind of makes sense that if you're trying to figure out the area underneath the curve, the smaller you make kind of the delta x or the delta t, of course, the better it will do. So, anyways, but as I said, that to use the smaller time steps, that's usually a lot more expensive and likely to get something to run well on an embedded processor that is connected and operating a machine like this by essentially controlling all 5 motors. The 10 to the minus 5 may only be achieved by like an FPGA or something like that, which is probably more expensive for hardware. I'm not sure. Maybe they've come down a lot, but certainly the process of creating it is more complicated too. And so anyways, I think we're still highly motivated to try other things to get it to work. All right. And so now I'm going to try TS of 10,000 or 10,000 hertz or TS of 1 e to the minus 4. So 10,000 calculations in 1 second. And that's where things got kind of interesting. And so anyways, let's again hit the run button. And things are going to be looking pretty good. Do you see that rattle though? And then all of a sudden, all bets are off. Everything's really broken, right? And so I'm going to bring you to that. So we're like right here. Again, I'm going to even box zoom on it so we can kind of see it really clear. And the first thing to go is really that hand motor. All right. And I could scope all these things and I could show that, perhaps on error of this is the first one that gets big, but I'm not going to worry so much about it. And so hopefully you're with me and just saying, yeah, the problem is that hand controller. You see it right there. It's this PID that's going to, I'll say, contribute the feedback adjustment on the torque that will be delivered through that hand motor, right? And so you go ahead and use the tuner. So on the PID block, the parameters here, there's that tune button, and it launches this. So welcome to the PID tuner block. It's one of the best things. We have a lot of really good things, so I don't want to say it's unique in this, but it certainly is one of the best things I think that I like to show with MATLAB and Simulink, right? And so the basic idea is it's going to figure out what KP, KI, KD, and N are, and then it's going to give you some measurements on how are we doing through things like rise time, settling time, overshoot, even like gain and phase margin and stuff like that. And in general, you'll see those numbers are small, and I'll just say, and it's acknowledging it's already unstable. So my process is just increase the gains until you begin to get something that's finite. Now maybe give it one more, maybe one more. And that looks pretty good to me, and I will update the block. So those numbers are now in here, and I click on OK. Oops, this is the unstable one. There it goes bad. And let's hit the green button up here and rerun it. Okay, and so now we're good. Okay, so wrapping it all up was a little harder than I thought. All right, and so if you are really observant, you may notice that today is the day after the 10 and a half minutes that you just watched. Okay, so anyways, I gave it a little bit of thought, and so I wanted to really kind of be proper in the way I summarize this, right? And so obviously we got this to work as we really kind of figured out the right rate to operate our feedback loops. We kind of, I'll say arbitrarily, but I think again, an informed arbitrary decision, okay, that 10,000 hertz is really a good number. And I know that because I work with enough customers who are doing motor control, right? So anyways, it turned out our goal was let's get the robot to work at 10,000 hertz, right? Now, what we came up with was a pretty cool trick that we were able to notice that the instability was really forming in really the control of the hand, which is really the rotation of this kind of final end effector piece. And so we tuned it up with the PID tuner. It worked beautifully, and we got the whole thing to work. Right. And so what I want to now be kind of careful as I summarize this is that this is this comprehensive approach. And what we're really seeing is an exemplary approach, right? And that to really get it to work right, it may take a few ideas. And one of them that worked real well on this occasion was the tuning of that hand. But earlier in that video, we saw that, well, if we do implement this perhaps with FPGAs and operate the voltage control or operate the torque control at 100,000 hertz, that will work as well, right? And I'd say that there are probably other ideas out there that we could bring in to get it to work. And certainly uh, the idea of MATLAB and Simulink as the platform for doing this, well, it's because it accommodates so many of the approaches of the general kind of, I'll call it categories of people that can kind of come in with their specialization and really make it work. Certainly there are people who know feedback control way better than I, and if my little tuning with the PID tuner did not work, I'd probably go to some of them, and a lot of them happen to work at MathWorks. Okay, so that's point one. Point two is we came up with a very simple, I'd say, requirement on what would define this to be a good robot, and that it basically did like 2 or 3 rotations, and it ended up in the position we're in right now. All right, and so again, my experience with so many of those great engineers out there using Simulink to develop systems like this. Well, instead of that one simple motion requirement, and maybe application for the robot, they often have thousands of them, right? And so for those 1,000 trajectories, I think they're doing a much more comprehensive exploration of the capability of the robot, and they're also really kind of, again, qualifying, certifying, making sure that this is capable of handling the overall mission expected for this robot. And so that's the truth and the reality of this. And so I'd say there are a couple of things there. One is the idea that you identify requirements, that you document them properly, and that you essentially hook up your simulations to things that contain those requirements. And so there are things like, was it JAMA, and then doors, and there are various requirements management tools that we do work with. All right, so there's that idea. There's the idea of creating a simulation that's close enough to the real system that we trust when the simulation meets a requirement that we have high expectation it will work with the real system too. And so that's part of it too. And then of course the creation of tests that will adequately kind of confirm or verify that the robot's passing each of those requirements. And so I think you're perhaps seeing where this goes, but it means that you're running loads and loads of simulations, and perhaps you're doing parallel processing. Maybe you're running it on AWS or Azure, and perhaps you're writing a very good, I'll call simulation report that's going to really tell you the status of your system against what your requirements are going to be requesting as you go through the various design processes. And everybody knows as soon as you put in a design feature, you're going to break probably like 5 of your other features. And so that whole um, process of adding features and making sure it works with the rest of the system is certainly enhanced and quite often facilitated by a real good simulation platform. So anyways, I kind of like what I just said. I'll kind of watch it and make sure before I kind of post this, but that's the general idea of simulation. And hopefully this example, you know, of going from, you know, continuous mode to discrete is a good example which says, hey, I just put in a critical feature for this to really work. And that we saw that in this specific example, that we did break things, but we were able to fix them very rapidly. So anyways, thank you.